Hey guys, sorry that this lecture is coming at you a little bit late, as has been for the whole semester. Things are crazy. Teaching 3 different classes, it's really hard to keep up with online stuff and in-person stuff. Plus, I was technically off on Thursday and Friday of last week. So, anyway, here's the lecture. Sorry it's late. It'll be okay. We talked last lecture about magnetic fields kind of qualitatively. Today we're going to be talking about them more quantitatively. They are measured in Tesla. This is a lovely picture of Nikola Tesla right there. Kind of a creepy picture, chosen on purpose because I thought it was a little bit funny. But anyway, I don't know a whole lot about the dude. I know that everybody says he's better than Edison and he invented alternating current, and that's about it. Go research him if you want to. But he's not super important for our topic here. Other than that, the unit for magnetic field is named after him because he worked with some magnetic fields. Something to note is that 1 Tesla, the unit Tesla, is a huge amount of magnetic field. Like particle accelerator magnets are on the order of 4, 5, 6 Teslas, and Earth's magnetic field is on the order of 30 to 60 micro Teslas. So 1 Tesla is a huge deal. Your fridge magnet says I got this information from Google, but fridge magnets are evidently about 10,000 micro Tesla. So today I said we're looking at it quantitatively, and don't freak out just yet. But we're going to calculate numerically the field value from a current. And the 2 equations that define this in general, like for any situation, are Ampere's law, which is this top one, and the Biot-Savart law, which is the bottom one down here. Now note that these are crazy looking because this means gradient, which is like the slope kind of a surface in calculus. You've got an integral here over a curved path integrals. These things are like 3-dimensional vector calculus, which we're not going to be dealing with in this class. So I just wanted to show you that these are the general equations. They are used to derive all of the equations that we're looking at for various situations. We're going to look at the magnetic field based on the current from a straight wire, from a loop, from a coil, and from a solenoid. All of those equations can be derived from these 2. But you won't get to that until you take a physics-based class. That's all of them. A calculus-based physics class. So to calculate it algebraically, you're going to have to choose the correct equation for the specific case. And you'll have to use the idea that fields can be superimposed. Superimposed means that they can be added together, but these are vector fields. So we're going to be adding in vector form. So if you've got 2 fields and they're overlapping in some way, shape, or form, it is a vector addition that you have to use when you're superimposing, because these are vector fields, not scalar fields. Another thing that we're going to be seeing is the permeability constant, mu naught. The permeability constant is 1.26 times 10 to the negative 6 Teslas times meters divided by amperes. This is characterized by a material. The 0 or the naught here means free space, which is a vacuum. So there's nothing in there. Sorry, I always spell vacuum wrong. Like every time I write the word vacuum, I spell vacuum wrong. Anyway, so this is the permeability constant for a vacuum. And that's basically how the material alters the magnetic field. It is the equivalent to the electrical permittivity constant, E sub naught, which was like 8.85 times 10 to the negative 12, some number of units, I don't know. This one was called the permittivity constant. This one is the permeability constant. Don't get them confused. A side note about these constants that's really cool is that if you work with the previous equations and Maxwell's equations, the previous equations are part of Maxwell's equations, but if you work with Maxwell's equations, you can whittle it down into an interesting thing, and the interesting thing says that velocity equals 1 over the square root of the permittivity constant times the permeability constant. which is that. And if you type this into a calculator, you will actually get this V equals C, which is the speed of light, 3.0 times 10 to the 8th meters per second, which is a really weird result. And it is the result that led Maxwell to figure out that light is an electromagnetic wave caused by the propagation of electric and magnetic fields, and that it propagates with this speed C, which broke open physics. It was crazy what that did for physics. It changed everything. And one of the things that it motivated was that this constant, or these two constants, don't change for based on the reference frame. And if you know anything about relativity, it's all about relative frames, inertial frames, and relative motion. But these two constants don't change relative to anything. So Einstein used this to motivate his arguments for the speed of light being the ultimate speed in any reference frame, which is a crazy mind-bending concept. And it all came from just these two little constants, the permeability constant and the permittivity constant. It's really cool stuff. Anyway, enough about that. We're just going to be plugging the numbers in here for the permeability constant, 1.26 times 10 to the, negative 6. Yep. Okay, so this equation here is for if you have the field from a straight wire. So we know from last time that a straight wire with a current running through it generates concentric circle magnetic field going around. And if the current's going to the right, you can use the right-hand rule to say the direction of these is going out of the page at the top and into the page at the bottom. So field is dots up here, X is down here. And the magnitude of that field is given by this equation. The B field equals mu naught, the permeability constant from up here. That was supposed to be a star, rip, times the current divided by 2 pi r. Now the r here is the distance from the wire to the point you're looking at. So you could look at a point really close to the wire where r would be really small, so field would be really big. You could look at a point really far away where r would be large, so the field would be smaller. And you can see from the equation that as you go out further away from the wire, that the magnetic field gets weaker, which is what you would expect. So here's an example of using for that equation. And we're also going to have to use the superposition principle, superimposing things, however you want to say that, where we take the two fields and add them together. So first up, we're going to look at wire 1. So wire 1 has a current going to the left. The first thing we should do is think about the direction the field is going. If you use right-hand rule, you point your thumb to the left, using your right hand, of course. Point your thumb to the left, curl your fingers around, and you'll see that at the bottom of the page, or the bottom of the wire, underneath the wire, we're coming out of the page, which looks like a dot. I'm going to draw these in blue. And that is everywhere along the wire. And then on top, it's coming out of the page. So we'll do some nice, lovely little X's. Cool. And we could calculate that numerically for the point P, where things are still coming out of the wire. Not out of the wire, sorry, out of the page. We can calculate at point P the field using the equation. Field equals mu naught times I over 2 pi r. Now I here is 5 amps. Mu naught is 1.26 times 10 to the negative 6 with some units. 2 is 2, pi is 3.14, however many digits you want to use. 3.14 is sufficient. And then r is the distance from the wire to the point, which is 8 centimeters. You got to convert that to meters to get 0.0 8. Cool. So you can plug that in and you can find a number. I'm going to call it B1. I'm not actually going to calculate that right now. You are welcome to do so, but I'm not going to. All right, on to wire 2. Wire 2 has current going to the right, so opposite direction. So you would expect field directions to be opposite, and right-hand rule confirms that. Point your thumb to the right, curl your fingers around. You see at the top of the wire, we are coming out of the page, which is a bunch of dots. And underneath the wire, we're going into the page. So right here between the two wires, you would see that these fields would add because you got going or coming out of the page, coming out of the page. But everywhere else, they're going to subtract. And something you should do that I'm really bad about not doing, but you should do it, is define, like you would a coordinate system for vectors, you would define going into the page as something, going out of the page as something. So I'm going to say going into the page is negative, coming out of the page is positive. So for wire 2 at point P, you've got a field that's going into the page, or sorry, coming out of the page. It's a dot. Whereas from wire 1, it's an X going into the page. So we're going to have to take the thing that's going out of the page and subtract it from the thing going into the page. And you calculate it using your formula. You would say that the field from 2 equals mu naught I, which is 5 over 2 pi, and radius now is a total of 16 centimeters, which is 0.16, which is 2 times the radius previously. So the field from wire 2 is half the field from wire 1. You would subtract and give it the appropriate direction, which, since wire 1 is bigger than wire 2, not size-wise but field-wise, at that point, we're going to say that it is going into the page. Next two are for current loops. And this applies, big thing right here that you have to make sure you know, is this applies only at the center of the loop. Cannot emphasize that enough. That is only at the point in the middle. Everywhere else you've got angles happening, all sorts of trig, weird things with superposition. We're only doing the middle, and this is the only place that equation applies, is at the middle. And it is mu naught times I over 2 times r. This r is the radius of the loop. Something that's kind of like an unstated, not rule, but just an unstated convention that's used in physics is that if you see a little r, that is a radius that you are measuring to a point. If you see a big R, that is a radius that is a property of some object of your system. So if you're looking at a sphere, it's going to have a big radius r. If you're looking at a distance away from a sphere, it's going to be a little r. So here we've got a big R, which means the radius of the loop. Now if you take a bunch of loops and put them together so that they're very, very tightly packed and your coil is very thin with n number of loops in your coil, it is that same equation as last time, but times n for the number of coils. It's basically taking all of the fields for each loop, the field for each loop, because they're all identical, and adding them all together, so multiplying by n. And this is a bit of an excessive example for this, but we're going to look at it anyway. This is a real thing that scientists did. They took some turtles and they put them in a magnetic field to see if it messed with their navigation. And if it did, that would prove that their navigation system was based on magnetism. So the way that they ran this test was they made a pool for the turtles to swim in. I'm going to make the pool blue. Here's the turtle pool. They wrapped a bunch of wires around it. I'm going to make the wires red. Picture not to scale. That's not the appropriate number of wires. Also, they probably weren't all crossed over each other because danger. And the magnitude of this had to cancel out the Earth's field, which was at 60 degrees. So you got to do a little bit of right triangle trig. You say that's the vertical component. The field is, let's see, 50 microteslas. That's 50 times 10 to the negative 6 teslas. And it's 60 degrees below the horizontal, which makes it 30 degrees from the vertical there. So you can do 50 times 10 to the negative 6 times, let's see, we're looking for y, which is the adjacent, so it's cosine of 30 equals your y component of the magnetic field from Earth. So that's how much has to be going down, or that's how much is going down. Sorry, I can't speak. We're trying to generate a magnetic field going upwards to exactly balance that out. To exactly balance that out, we'd have to have 50 times 10 to the negative 6 cosine 30 going up, which equals previous equation, permeability constant, times the number of turns, and that is given to us 60 turns, coil of wire, times the current. We're looking for the current in the coil, divided by, I think it's 2 times the radius. This is a 72 centimeter diameter, so that's 0.72 centimeter diameter, so we could divide that by 2, multiply by 2, make this bottom thing 0.72 meters, solve that for current, and you know the answer. And this is a pretty interesting question just because it's based on an actual scientific experiment, and it's important to think about experimental design, especially if you're going to go into any STEM field, particularly one of the pure sciences like biology, chemistry, physics, if you're going to be doing research, because taking all of these equations and using them to solve for a variable in a free response question on an AP test is one thing, but taking that knowledge and applying it in the field is entirely another. So I think it's a really good framework for a question is to have it in terms of an experiment that someone has actually done and see how you use these equations in the real world. And I don't remember what current you get here, and I'm not about to multiply it all out, but it's somewhere between, like, I can't remember if it's the one that's like a decimal on the order of tenths or hundredths, or if it's one that's more like 14. But the current you get should be something that's achievable. And if it's not something that's achievable with the equipment that you have to do your test, then you can figure out some other parameters, like maybe looping it more times or getting a smaller diameter, something like that. So it's really good to think about questions in terms of experiments. And the last one we have to look at is a solenoid. A solenoid is really cool because it makes a mostly uniform magnetic field in the center. And a solenoid is the same as a coil. It's got a bunch of loops, n number of loops, but they're kind of further spread out. They're not as tightly packed. The assumption with the thin coil was that they were so tightly packed that we could superimpose them without any issue. Now they're spread out enough that you can't superimpose them all at once the way we just did. So it changes things a little bit. And the new equation you have here is that the field is mu naught times n I over L. I is the current, n is the number of turns, and L is the length of the solenoid. Note that this does not depend on the radius of the solenoid, which is crazy, and also that this applies to the field anywhere inside the solenoid. It does not apply outside the solenoid, but it does apply anywhere inside. You don't have to be in the middle like you did with the loops and the thin coil, the tightly packed coil. With the solenoid, it is uniform anywhere inside. Now you can notice over here in the field lines on the edge, it gets a little bit weird. We're ignoring edge effects for now because it's not something that we are equipped to calculate. But here's an example question for you. It says an investigator needs a uniform 30 millitesla field, which she intends to produce with a solenoid. She takes a long 10 centimeter diameter tube, wraps wire along the length of it, wrapping 1,200 turns of wire along a 75 centimeter length of the tube. How much current must she pass through the wire to produce the desired field? So really this is just plug and play. You're trying to get a 30 millitesla field, which is 30 times 10 to the negative third. which is equal to mu naught, it's 1.26 times 10 to the negative 6th, times n, number of turns, 1200 turns, times I, we're asking for current, over L, which is 0.75 meters. Note that the diameter here is irrelevant because the field of a solenoid does not depend on the diameter. And you just calculate this out, find I. I think this is the one that's like 14 point something, which is a fair amount of current. But it's achievable. So this would be fine for an experimental design. All right, last problem. Try to see if you can do this one on your own. Something to think about here is that you've got a straight wire and you've got a loop, so you're going to have to find the fields from both of those, superimpose them, be sure you check directions before you add them together to make sure they're going the same way, or to subtract if they're going opposite ways. So try this one on your own. Let me know if you have any questions or concerns. Again, sorry that this lecture is coming at you late. Doing the best I can. Please have patience.